Alright, so in this video I'm going to be talking about weak Fourier transforms. There's something that you should learn about if you're interested in pursuing anything like physics, economics, or mathematics. I'll be giving an approach to Fourier transforms which is primarily motivated by the desire to solve linear differential equations, and it will use contour integration in the complex plane. So the complex plane, hopefully you're familiar with it. It's the set of all complex numbers as a field. It's equipped with addition and multiplication. And regarding this field, we're going to be talking about a specific function, which is the most important function probably in all of mathematics, the exponential function, which is a map from the complex numbers to the complex numbers. And it's defined, can be defined in many equivalent ways, but the standard definition is given by this Taylor series. We're defining negative factorials. 1 over the factorial of a negative integer is going to be 0. So this sum is actually over just the non-negative natural numbers. You can ignore the negative factorial terms. You can also write it as e to the x. This is more of a notational definition. This symbolism here refers to this infinite series. The cool thing about the exponential function is that it's an eigenfunction of taking the derivative, which means if you take the derivative, which here I'll write taking the derivative as an operator, d sub x means take the derivative with respect to x. If you take the derivative with respect to x of the function e to the x, you'll just get e to the x back. All right, and you can use this as a starting point for defining this infinite series. What this means is, using the chain rule, we can use composition of functions to determine the derivative of any composition of the exponential function with a linear map. So more specifically, if you have the derivative with respect to x of e to the lambda x, where lambda is a scalar, this is going to just be lambda times e to the lambda x. Once you have this, it means that taking the derivative of exponential functions is extremely easy. You can just replace the differentiation operator with multiplication by a scalar. What it means is, just like in linear algebra, is if you write an arbitrary vector as a sum of eigenvectors over a particular linear operator, then applying that linear operator becomes very easy, because now you just apply it to each of the individual terms. In this case, differentiation is a linear operator because we know that this equation holds. So basically it distributes over both addition and scalar multiplication, and that's what makes it a linear operator. So what that means is, if we can write an arbitrary function as a series of exponential functions, then taking the derivative of that function is going to be very easy. If we were to write f of x equals sum over some parameter lambda of some scalars times exponential functions, right? So this scalar is parametrized by this same lambda, which is giving the scalar in the exponent. If we write this, then that means the derivative of f of x is just going to be, basically you copy the same sum except for you bring a lambda down, right? Because, well, this is not actually always true. This is not being extremely rigorous. We still have to talk about convergence. But if this converges, then this series is going to be the derivative of this series. You can also take arbitrary derivatives, right? If I take the derivative again, I'm just going to pull down another lambda. So if I take the nth derivative, then lambda is just going to be raised to the nth power. So not only is taking the first derivative easy, taking successive derivatives is extremely easy once we have this form here. Right? And like I said, we're trying to solve linear differential equations. So if we can take derivatives of a function very easily, that means we can basically express the linear differential equation as a linear algebraic equation. Because now instead of taking derivatives, we're just multiplying by a constant. So what we're going to do then is we would like to be able to decompose a function this way for any function, but a priori we have no reason to believe that that's possible. So instead, what we're going to do is just assume that a function can be written in this form. By doing this and by operating on both sides here, we're going to figure out what those coefficients have to be, and that's going to give us the Fourier transform. We want to isolate an arbitrary coefficient because we want to be able to solve for each coefficient. So what we're going to do is multiply on both sides by e to the negative jx, where j is some other value in the same space that this parameter exists in. So what we're going to get is, well, if lambda is equal to j, then this is e to the jx, and we're multiplying by e to the negative jx. So the exponential part's just going to become 1. So we're going to have a term that's just c sub j. And then we're going to have all of the rest of the terms. So where lambda is not equal to j. And now we can solve for cj. We haven't really done very much. Maybe this was not what you expected to happen, but this is valid. It's true. I mean, all we did was multiply by e to the negative jx on both sides and subtract this sum, assuming that it converges, right? So we have this. And this doesn't really look like it's going to help us very much, because here we have one coefficient, but then we have this formula for it that involves every other coefficient. So that's not very useful, seemingly. But we can actually get around this problem because of some properties of this function here. The exponential function is very special because it's analytic, which means that it's basically equal to its own Taylor series, which is how we defined it. So because it's defined as a Taylor series, it's automatically analytic if it converges, and it's easy to prove that this thing converges. But analytic functions can be integrated in the complex plane by just evaluating its antiderivative at the endpoints in the complex plane and subtracting, right? It's just like ordinary integration, except for instead of over the real line, you're doing it over a curve in the complex plane, and that curve is called a contour. So this is going to be a contour integral. What it's going to look like is, let's say here's the complex plane, and we have this point A and this point B. Then there might be some contour going from A to B, like that. And what we're going to do is integrate this function from A to B If that function is analytic, then if we know that its antiderivative is f of x, so let's say the derivative with respect to x of f of x equals little f of x, right? Then the integral from a to b of little f of x dx is going to equal f of b minus f of a. Right? It just looks like the standard fundamental theorem of calculus, but it applies not only to integrable functions on the real line, it applies to complex analytic functions over contours in the complex plane. So this might not seem helpful, but you'll see how this is going to help us solve this situation. All right, so there's one more piece of information about the complex exponential function that's going to be important for us, and it's that the exponential function is periodic. So not only is it analytic, it's periodic. And what I mean is that there's a number such that if you add it to the argument of the function, you're just going to get the value of that function at that same argument back. In other words, exp of x plus some period, which the period of the exponential function is 2 pi I, equals exp of x, right? So the function is periodic, and that's going to help us solve the problem that we had on the last page. So what we're going to do, well, the equation that we had was Cj, it's true for all j and all x. I'm going to apply a function on the left side and apply that same function on the right side, and since it's a function, the equality is still going to be true. The function might look a little weird, but you'll see why it's useful. First thing we're going to do is multiply through by an arbitrary function. It doesn't matter what the function is, okay? We'll see what kind of function we might want it to be. We're going to multiply by just some arbitrary function, g of x. And now what we can do is actually just integrate on the left and on the right over some arbitrary contour in the complex plane. So this contour I'm calling gamma. So once we have this, we can just pull out Cj, but this part, we can pull out the sum from the integral and the minus sign. So it's going to be the sum over this, and we can also pull out the scalar. So it's going to be, okay. And we have this equation now, right? And if this thing is not 0, then we can divide by it and solve for Cj, right? So, and if it is equal to 0, then we can't get any information about Cj. So we need this thing to be non-zero, right? So that's the first thing we need. Step 1, we need this integral to be different from 0. Okay. And now here's the more interesting part. If you look at this here, we're summing over lambda not equal to j, but if somehow we could make it so that for every lambda not equal to j, this integral is equal to 0, then we'll have gotten rid of the dependence on these other scalars, right? So the second thing that we need, and then we'll have just the equation for c of j, right? We'll just take this integral, divide it by this integral, and this part will be 0, so we'll just be left with Cj. So the second thing that we need is for this integral, so for all lambda not equal to j, right, we need this integral to be equal to 0. So this isn't a necessary condition, but if we find these two, if we find a function g and some contour gamma that satisfies these two conditions, then we know what c sub j is, right? And it's actually very easy to come up with a solution to this. Well, easy is relative, but basically you can just kind of guess and check. But because this function here is periodic, with that, and its antiderivative, since e to the x is an eigenfunction of taking the derivative, the antiderivative of e to the x is going to be related to this function. It's also going to be periodic. So what we can do is just set g of x equal to 1. We didn't actually need this function g of x. So let's take g of x is equal to the constant function that's equal to 1 everywhere. So 1 is automatically satisfied as long as the contour is non-trivial. If the contour is just between a point and itself, then it's going to be 0. So we want a contour between 2 points, let's say a and b, where a and b are different. And we're going to take g of x equals 1. So this satisfies the first condition. Now we can look at the second condition. So g of x is 1. Gamma is some integral from a to b. So, and lambda is not equal to j. So we know that this integral becomes, oh sorry, and this has to be equal to 0. I didn't write that down, but I said it. So this has to equal 0. And what that means is that we have some contour integrated over of this function here, g of x is 1, and this is just going to be e to the lambda minus jx dx, and that needs to equal 0. Well, this is extremely easy to take the antiderivative of. When you do this, you'll find that it's e to the lambda minus j b over lambda minus j minus e to the lambda minus j a over lambda minus j. And that has to equal 0. And notice that we can divide by this because we're only looking at the case where lambda is not equal to j. So these are never 0, right? Okay, so what that means is that, well, because it's non-zero, we can just get rid of it, right? We're just multiplying by this same thing on one side or the other, and it's equaling 0, so we can just cancel that part out, and we get that e to the this thing is equal to e to the that thing. So we have to have e to the lambda minus j b equals e to the lambda minus j a, right? Okay, so what does this mean? Well, since the exponential function is periodic, it means that these two arguments, lambda minus j times b and lambda minus j times a, have to differ by an integer multiple of the period. And that means lambda minus j b minus lambda minus j a is equal to 2 pi I times some integer, right? Or it's in this set. This set is the set of all integers multiplied by 2 pi I. And you can rewrite this as lambda minus j times b minus a. So this has to be an integral multiple of 2 pi I. Okay, but that means we can, so we assume that we fixed j, right? And we have this contour from a to b. So let's solve for lambda. It means that lambda has to be of this form, where you take j plus 2 pi I divided by b minus a times an integer, right? So that sum that we were summing over the parameter lambda now is actually a sum over numbers of this form. We have no other restrictions on lambda other than this. So we can just impose that restriction on lambda, and there's really nothing stopping us from doing that. So what we find is that Cj, so this basically this contour and this function satisfy the properties that we want. So now we have an equation for Cj. And when you do the algebra and cancel out the term that's 0, it looks like this. So you can already see it's looking like a Fourier transform. And this is true for all j. So we have an equation for the coefficients, and it's just an operation over this function and some contour. It doesn't even matter what b and a are. You can choose any a and b as long as they aren't equal to each other, and this is always true. So what we can do is basically take this original equation that we assumed, right? We were adding over all lambda, c lambda, e to the lambda x, right? And we know that lambda is of this form, right? So lambda is equal to j plus 2 pi I over b minus a times some integer. And what that means is that our indexing is over the integers. So let's say we're indexing over n, right? Then this c sub lambda is going to be c sub j plus 2 pi I over b minus a times n, right? That's just the formula for lambda, right? Each value of z indexes a particular value of lambda that's possible. So we're just substituting that in for lambda. And we also have a formula for c sub whatever, right? This is c sub j equaling this. So we can actually substitute this in for c sub that. And, well, we still need to multiply by e to the lambda, but lambda again is just j plus 2 pi I n over b minus a times x. Okay, so this is what was on the last page. I just copied it down so that I can copy it here more easily. So we also have that formula where c sub, and I used j before, but because it's arbitrary, I'm going to replace it with m, right? So c sub m is equal to 1 over b minus a times this integral e to the negative mx times, and actually, because it's an integral, I'm going to replace it with a different variable just so we don't get confused. Okay, so the integral originally was over x, but it's a dummy variable, so we can replace it with t. So this is the formula for the mth coefficient in the exponential expansion of the function, right? And we have this here. So this term here, which is lambda, that's now our value of m. So we're going to substitute this in for m. And then we have this formula that we can substitute back in for c sub m. So this becomes f of x equals this sum, right? And we're doing c sub this. So I'm just going to copy this and replace m with this term here. That's the coefficient. That's just c sub lambda right here. And then we need to copy this part. So that's times. So we have this now. And if you notice here, we're basically applying some operation on f, just a function, and then we're doing some more stuff to it, and we're getting f back, right? So there's f. We do stuff to it, we get f back. That means that whatever we did to it, we would have done some transformation and then the inverse of that transformation, right? So basically, we can write this. So let's call this part that I put in brackets some operator of f, right? So I'm not going to beat around the bush. I'm going to call it a big F for Fourier, and I'm going to operate. It's going to take functions of x and map them to functions of n. I'm multiplying by this exponential function, and then I'm integrating over a certain range, right? So this operator is indexed by a, b, and j, right? So there's 3 variables that are free. So this isn't the Fourier transform, it's a Fourier transform. And its inverse is given by this. Okay, so these are already looking like Fourier transforms. This is just right off the bat an integral. You can see it. This is going to become an integral. It's actually of the form of a Riemann integral. This 1 over b minus a is going to be the dx, right? If we replace this 1 over b minus a equals like delta w or something, then this would be n times delta w. So we can just do that right now. So if we set w equals n delta w, where delta w equals 1 over b minus a, then this is going to equal n is equal to w over delta w. So this is going to be, if we define a new function, so let's call it f hat or f bar of w is equal to, right, that'll give us the value of n that corresponds to w. Then this is equal to f bar w times e to the j plus 2 pi I n delta w, which is just w. So 2 pi I w times x. So you can see that this is basically already an integral. As delta w goes to 0, this becomes an integral. And we can see already that they're inverses of each other, right? So this is a Fourier transform, and this is an inverse Fourier transform. And that's basically all I wanted to show. You can go further with this, and you can derive the standard Fourier transform by selecting a and b to be numbers that are real and going to positive and negative infinity. And you can, since j was arbitrary, you can just set j equal to whatever you want. If you set j equals 0, then you get the standard Fourier transform. So that's all. Thank you for watching. I hope that it made sense, and take care.